Hello again. So in the recent recordings, we've been talking about electric potential energy, and such things like that. And I've sort of been talking about them, about these concepts in the abstract. Just sort of, here's how you calculate electric potential, here's its relation to electric field, but haven't actually applied it to any physical system. And that's because in order to do that, we need one more additional set of concepts. And that's what I'm going to do for you right now. Broadly speaking, although you've seen that electric charges, the electric fields they create, the electric potentials that they create, can happen on both insulators as well as conductors, conducting materials. My current interest is in electric potential, electric fields, and conductors. And the reason for that is that what we're going to do once I get through just a couple more concepts is start constructing actual electrical and electronic devices, at least in theory, and we're going to analyze those. And to where we're heading with this is we're going to start thinking about and analyzing circuits, which are, of course, constructed from conductors. So I'm going to focus our attention now on conductors, and I want to talk about properties that conductors have, how conductors react to and affect both electric fields and electric potentials. So I'll just remind you that in an insulator, although it's possible for the charges or the charged molecules to rotate, as a general rule, they cannot and do not move. They don't translate. On the other hand, in a conductor, the charges are free to move with very, very little resistance. And we're going to study resistance in some detail in days to come. But in any case, as a side note, by the way, the charged objects that are moving in a conductor don't necessarily have to be just electrons or protons or single point particles. In a battery, for example, typically they are electrically charged ions, often sodium ions and chloride ions and various other things like that. Hydronic acids and various other things. So let's talk about conductors just in general, and as I say, their various properties. Okay, first off, so I'm going to list, there's a number of properties, I'm going to list them off. And number one. First property, the electric field is zero inside a conductor. How can that be? To make that clear, let me draw you a picture. So what this is, oh my God, it's like three-dimensional drawing there. So I want you to imagine that as a slab of metal, slab of aluminum or slab of copper or something like that. It's electrically neutral, we will assume. And of course, what that means is that not that the object doesn't have any charged particles at all, but rather that it has equal numbers of positive and negative charges. In this case, since if we're imagining it's actually copper, then the charged objects are protons and electrons. And it turns out, and I think we've discussed this before, either in these lecture videos or in class, but in any case, in real life, it is the electrons that do the moving, and the protons tend to stay very much in place, and that's due almost entirely to the vast difference in mass between the electron and the proton. So the electrons having 1,835 times roughly smaller mass than the protons are affected, that is to say the gain in acceleration that is 1,835 times larger than the acceleration that the proton gains for the same electric force. So the practical upshot of that is that for all intents and purposes, the protons in this slab of copper are not going to move essentially at all, and it is the electrons that will do all the changing of position. So to start off with, just putting this slab here, the charges inside the copper will automatically arrange themselves so that the net force among them is zero. The net force on all of the charged particles is zero. And that will happen while there is any net force acting on any of the charges at all. Because if there is, they'll keep moving. And eventually, and by eventually I mean within nanoseconds, they will find an arrangement where the net force on all the particles vanishes. And when that's true, the charges, well, if there's no net electric force, there is ipso facto no net electric field either. So first of all, the electric field is zero in that situation. However, we can go further than that, because suppose I then immerse my slab of copper in an external electric field. So some other field that's created by some source charge that we don't see, that we don't know, that we don't control, but it exists. And so just for simplicity, it doesn't actually change the argument any, but I will make the external electric field here uniform and entirely horizontal. Again, it doesn't have to be that way, but it's a little bit easier to discuss if we do it like that. Okay, so there's the external field. I hope you can see that in the drawing, horizontal external field that way. Now, in the presence of this external field, now this external field will create a force on the mobile charge objects, the electrons in this case. And the electrons, remember, are going to move in the direction opposite the direction that the electric field points. And as a consequence, they will tend to pile up on the left side of the slab of copper. And since the electrons moved but the protons did not, the electrons will leave the positively charged protons behind, and so the right side of the copper ends up with an overall net positive charge, not because it gained any positive charges, but because the negative charges that were originally here got shunted over to the left. Okay, and the result of that is an electric field created by this new charge distribution that it was induced by the external field. But notice that this internal field, as I will call it, points, of course, from positive charges towards negative. So that means that the internal field points from right to left. E internal, I guess I'll call it. And the significant thing here is that this induced internal electric field points in the opposite direction of the external field. The result of that is the internal field tends to cancel the external field that induced this polarization of the charge inside the copper. And this process of the redistribution of the charges inside the copper is going to continue as long as, just like I argued before, as long as there's a net force on the electrons here, they'll continue to shift over to the left. And only when the net force on the electrons vanishes does the redistribution of charge stop. But the net force on these electrons goes away only when the entire electric field inside goes away. And that happens again because of the internal field. So the internal field canceling the external field in the space inside the copper slab. So the short version then is the external field shoves the electrons over to the left. That builds up an internal field which tends to cancel the external field, and the redistribution process continues until the internal field is equal and opposite to the external field. And when that happens, the net field is zero, and once again, the electric field inside the conductor is now zero. Okay, so no matter what you do, you're going to end up with electric field of zero inside of a conductor. And of course, if you turn off this external field, these piled up charges immediately redistribute themselves and make the internal field vanish once again. All right, second properties. Okay, so the second property of conductors says that the net charge density inside the conductor is zero. This actually is almost an automatic consequence of the first analysis, and it's pretty simple. Remember that what causes an electric field in the first place is the charge and the distribution of the charge. Well, since the electric field inside the conductor is zero, then there is no net charge distribution, no net charge density inside the conductor, because if there were, there would be a field inside. Again, no, I'm not saying there's no charge inside the conductor. There's lots of charge in the conductor. I'm not even saying that the charge hasn't distributed itself in some way. Of course it has. I just described that. What I'm suggesting is that the arrangement of the charge produces a charge distribution that results in overall no electric field, and so as a practical matter, the charge distribution that you have essentially sums to zero. And if that didn't make a lot of sense, focus on the statement that what causes an electric field is a charge distribution. If I don't have an electric field, then my charge distribution is effectively zero. Okay. Yeah, I think I'll just leave it at that. Once again, it's basically there's still just as much positive as there is negative, and so the net charge is zero. Okay. Now, I could, for property number 3, I could, of course, add external charge if I wanted to. We've done that several times during the course of the quarter. And I could artificially have some source of charge, rub a plastic rod and touch the conductor, and charge would transfer from either from the rod to the metal or from the metal to the rod, whatever. I could get I could imbalance, I could unbalance the charge. And if I do, then we end up with a net charge on the conductor. And if that happens, if we artificially cause an imbalance on the charge of the conductor, then that net charge will reside on the surface of the conductor. Explanation? I argued in step 2, or property number 2, that the electric field, the net electric charge density inside the conductor is 0. Since there's no net charge density inside, if there's any excess charge, there's only one other place it can be, and that's the surface. Okay, easy enough. Okay, property number 4 is very important. Okay, the electric potential is constant everywhere on a conductor. Actually, I can go further than this. It's not just on a conductor. It's also inside. Okay. This follows from the relationship between the potential difference and the electric field. So remember that the potential difference, so let me do this. There's my copper slab. I've rotated on its side, I guess. Okay. And let's choose 2 arbitrary points, label them A and B. Okay. And I'll say, okay, the potential difference between points A and B is equal to, well, let me start off, make it clear that point A is actually, points A and B are actually inside the copper slab, inside the conductor. Okay. So the potential difference is, if I can write as delta V, is the difference between the potential at point B, the potential at point A, but that's equal to just the electric field inside times delta L, and delta L is that. Okay. However, I just argued in the previous property that E is 0 inside the conductor. Since E is equal to 0, so VB minus VA is equal to 0, which implies in turn that the potential at B is equal to the potential at point A. But points A and B are arbitrary. I just chose them randomly. So this argument holds true for any 2 points inside the conductor. Okay, and so what this says is the potential at this arbitrary point is the same as the potential at this arbitrary point. So any 2 points, the potential has to be the same, has to be equal, and that's what I was arguing. Okay. The argument for the electric field, the electric potential being constant on the surface is a little more involved, and to really make the argument, it actually requires some calculus, and I think that we'll skip lightly over that, so I'm going to ask you to simply take my word for it, that the potential is constant on the surface as well. Okay. All right. And finally, our last property. the electric field on the outside of a conductor, I'm going to get another pen here. The electric field on the surface of a conductor is perpendicular to the surface everywhere. And again, I'll make you a drawing for that. Okay, and I'm going to emphasize the point by drawing an arbitrary shaped conductor. Actually, I'll make you two drawings. So this oddly shaped thing is a random piece of metal. So it's a conductor. Okay. And I'm going to, my strategy for convincing you of this point is I'm going to argue the opposite. Okay. And let's say, so this is a conductor. Let's suppose that the electric field were not perpendicular to the surface somewhere. Okay. And so, for example, suppose I thought that the electric field, let me back up. We've talked about how the excess charge is going to live on the surface here. And so what I'm drawing here is excess charge. Okay. The charge density inside is 0, but so any excess charge has to be on the surface. Okay, and so let's suppose that the electric field were not, as I say, perpendicular to the surface somewhere. So I'm going to choose a random location and say, okay, suppose that were the electric field caused by the excess charge near this point. If this were, in fact, the electric field vector, then let's see what happens when I break this field vector up into two components. One component parallel to the surface at this location, the other component perpendicular to the surface at that location. If I do that, then I'll have a parallel component that looks like that, and I will have a perpendicular component that looks like that. Okay, so that's E perpendicular, and this here would be E parallel. Right? But this electric field, this parallel component, parallel to the surface at this point is what I'm talking about, and perpendicular to the surface at this point. Okay, so if it makes you happier, I can move this over here. But let's take a look at this parallel component. It is an electric field vector. Being a component doesn't change the fact that it's an electric field. And as such, this electric field vector would apply a force on all the other surface charges that are right next door to this particular charge. So let's suppose it's this one electron causing this electric field vector. Well, the other ones are crowded really close to it, and so they would be affected by this field vector. And in particular, this electron here would be affected by the electric field vector of its next door neighbor. Okay, and if this parallel component existed, the effect would be to cause the electron to accelerate in one direction or another. Okay, in other words, change position, to move. And it will continue to accelerate, continue to change position until the net force on it is 0. Okay, but the net force on the next door charge means that there's no electric field on it, or more correctly, this component vanishes. As far as the perpendicular component, we've already talked about how the charges won't move inside because of other things. And so the parallel component, the perpendicular component is not able to push the excess charges inside the interior of the conductor. And this parallel component, as long as it exists, it will cause these surface charges to move until the parallel component vanishes. And when that's true, all of the electric field vectors then have no parallel component, and so only the perpendicular components are left, which is what I argued. Okay? And the result is that the electric fields never look the way that I offer up, that I guess might. In fact, the electric fields, basically what happens is all the parallel components vanish, and the electric field vector everywhere, perpendicular surface, and so you end up with a conductor that looks like a pincushion. And so on. I'll just draw a few more to make my point. Okay. I'll let you fill in the rest. All right, so those are the properties of conductors. Just real quick, I want to point out that this particular fact is useful for protecting your house, because what happens is you build yourself your house, at the house. You can tell it's a house because there's a front door there. You can tell that's a front door because that's the doorknob. And you can tell that's a doorknob because I told you the doorknob. Thank you. Okay. And what about lightning strikes? You put up a lightning rod if you come from that part of the country. And what's a lightning rod? Well, a lightning rod is just a piece of metal, and I'm going to draw it, though the size is going to be a bit exaggerated here. But the lightning rod is a pointed object like this. It's a metal conducting material, and it's got a wire that connects it to the earth. And so this is called an earthing wire or a grounding wire. It's connected to the ground, it's connected to the earth. In the United States, we tend to call it ground wire. In other parts of the world, it's usually referred to as an earthing wire. Either way, ground, earth. Okay. And what happens is that if lightning hits your house, it's going to be attracted and hit the lightning rod and not your house. Why? Because for two reasons. One, this lightning rod is a conductor, and the roof of your house, generally speaking, is not, even though it's wet. This metal rod is a much better conductor. And as the charges build up in the clouds, you get a whole bunch of charge up here, essentially zero charge down here, and so you end up with a huge electric field, a huge potential difference, and that, of course, generates a huge electric field. But the electric field, as I was just suggesting, points everywhere perpendicular to the conductor. But notice a thing, that the electric field, and I didn't really emphasize it enough, so let me emphasize it here. Notice that the electric field lines are much denser towards the point of the lightning rod than they are anywhere else. So very strong electric field, that's where the very strong potential difference is going to be. And so when the charges move from the clouds down to towards the earth, they're going to, the force on them is going to send them to the lightning rod. And then the charges will move down the conductor, down the earthing wire, into the ground harmlessly and not destroying your house. And so, a whole bunch of theoretical properties of conductors turns into a very practical, very simple, very inexpensive way of protecting your house. Okay, now that we have a handle on how conductors work, we are going to then take this knowledge and apply it to our first electrical device, which is known as a capacitor. And a capacitor is going to be just two conducting plates close to each other, and it will turn out that those plates put that way are going to do a lot of very important and very useful and, frankly, a lot of very simple things. So that'll be in the next few videos.